July 13, 1943. Royal Aircraft Establishment, Farnborough, England. Wing Commander Derek Jackson, a physicist turned RAF officer, stands in a laboratory filled with the quiet hum of electronic equipment. Before him lies wreckage spread across 3 tables, not from a bomber, but from a German Liechtenstein BC airborne intercept radar, recovered intact from a Junkers Ju-88 night fighter that landed by mistake at RAF Woodbridge. The German crew believed they were approaching their home base in Holland. Disoriented and confused, they landed wheels up on a British runway and were captured before destroying anything. In the nose of their plane was the radar that had been killing RAF bomber crews for 2 years. That device had turned the darkness into a weapon. Since 1941, night raid losses had climbed from 3% to 12%. Mathematically, few crews survived 30 missions. Germany's secret lay in this machine, eyes that saw through cloud and smoke. Now, for the first time, the British had one intact. Jackson's task was to tear it apart, understand every circuit, and find a weakness. He was not a soldier by nature. Before the war, he studied spectroscopy at Oxford. Light, not war. But radar was physics, and physics had become the front line. He photographed every component, then began disassembly. Careful, methodical, scientific. The Liechtenstein BC was intricate. 4 antennas, a 490 MHz transmitter, and a 12-tube receiver of elegant German design. The transmitter worked perfectly. 1.5 kilowatts output, clean pulses, no faults. The receiver was the key. Inside were 12 AF7 vacuum tubes, beautifully made, low noise, high gain. Each tested flawlessly, better than any British equivalent. And yet, Jackson was uneasy. If the German radar was this good, why did any bombers make it home? He reassembled the system for a live test. At first, flawless performance. Then suddenly, the display flickered. The return signal dropped, then recovered. A few minutes later, it happened again. Voltages steady, connections sound. Still, the signal flickered. Brief, erratic losses. Jackson isolated each stage until only the amplifier tubes remained suspect. Individually, they worked perfectly, but in the operating radar, they faltered. He suspected vibration, the one condition his lab could not yet replicate. He built a vibration test rig, mounted a tube, wired it to an oscilloscope, and began shaking it. At low frequencies, it was stable. At 85 Hz, the output collapsed. Gain dropped 60%. He stopped the vibration. The tube recovered instantly. He repeated the test. Same result. Mechanical resonance. The internal structure of the tube vibrated at its natural frequency, changing the spacing of its electrodes and destroying gain. And 85 Hz matched normal aircraft vibration. Every time a night fighter hit that frequency, its radar went blind. The display still swept, but detection range fell from several kilometers to perhaps 1. Pilots blamed jamming or weather, never realizing the fault was within. Jackson wrote his report. AF7 tubes exhibit severe gain loss under vibration near 85 Hz. Detection range reduced by 70 to 80%. It explained why bomber crews sometimes escaped. The Germans weren't retreating, they were blind. Air Marshal Arthur Harris read the report twice, called a meeting, and listened as Jackson demonstrated the failure. How certain was he? Completely. Could the Germans fix it? Eventually, but not soon. Did they know? Unlikely. Then Harris asked, how do we use it? Jackson suggested evasive maneuvers to trigger the resonance in pursuing fighters. Harris acted immediately. Instructions went out secretly. When under attack, execute sharp turns and throttle changes every 20 to 30 seconds. Crews were never told why, only that it disrupted enemy tracking. By August 1943, bomber losses fell from 9% to 7%, then 6%. German pilots complained of disappearing targets, maintenance found no faults, and no one suspected vibration. Throughout 1943 and 1944, the secret held. Jackson's discovery remained known to a handful of people. Each night, bomber crews unknowingly exploited a flaw buried in German engineering. In Luftwaffe records, the complaints mounted: targets fading without cause, interference unexplained. Ground tests showed nothing. Nobody tested under flight vibration. The British kept the truth tightly guarded, sharing it with no one, not even allies. Each time a bomber escaped, the residents had likely saved it. By early 1945, Germany introduced the FUG-220 Liechtenstein SN2 radar with new tubes and different construction. Jackson tested a captured set and found the flaw gone. The resonant frequency had shifted above 200 Hz, beyond airframe vibration. But it was too late. The war was lost. After the war, Jackson returned to Oxford, resuming his spectroscopy research and earning a Fellowship of the Royal Society. His wartime work remained classified until 1958, and then passed almost unnoticed. He never spoke of it. Asked what he had done in the war, he answered simply, "radar research." He preferred not to think about the calculations that had translated physics into survival. The problem had been fascinating, the implications terrible. Both were true. In 1978, graduate student Peter Williams found the declassified reports while researching electronic warfare. He wrote to Jackson, now 74 and retired. They met in Jackson's study, a room of books and quiet light. The old scientist described the capture of the radar, the flickering signal, the vibration tests, and the moment he understood what it meant. "How many crews survived because of you?" Williams asked. Jackson paused a long time. "I don't know," he said. "Hundreds, perhaps thousands. Part me, part chance." "Do you feel proud?" "Proud, no. Satisfied, maybe. I found a weakness. Others used it. Lives were saved. That's enough." Williams published his dissertation in 1980. It drew little attention outside academia, but the story slowly entered history. A footnote here, a paragraph there. The quiet record of a hidden victory. Jackson died in 1982 at 78. His obituary in The Times mentioned Oxford, spectroscopy, and one line: "During the war, Professor Jackson contributed to radar development." Nothing about Liechtenstein. Nothing about resonance. Nothing about the crews who came home because he understood physics. Yet his method endured. Modern electronic warfare was built on it. Capture enemy technology. Test under real conditions. Find weaknesses. Exploit them. Digital or analog, tube or chip. The principle never changed. Test under stress. Observe failure, and learn truth. Every intelligence lab since 1943 has followed that pattern. From Cold War espionage to modern conflicts, engineers still do what Jackson did: push technology until it breaks and listen to what the failure reveals. Decades later, former Luftwaffe night fighter pilots wrote memoirs about radar frustrations. They remembered targets that simply vanished. For years, they blamed British jamming. Only when archives opened did they learn the truth. German engineers were stunned. The flaw was obvious in hindsight. A simple vibration test would have revealed it, but wartime urgency left no time for such details. Thousands of tubes were already built, hundreds of aircraft equipped, and there was no turning back. Today, Jackson's discovery is more than a historical footnote. It is a lesson in engineering humility, that systems fail in the real world, not in theory. Vibration, heat, and stress expose truths equations miss. A flaw smaller than a fingernail once altered the course of a campaign. Even perfection can hide a resonance. Some victories are loud, cities burning, armies advancing. Others are quiet, a scientist alone in a lab, watching a trace flicker and realizing what it means. Jackson's was one of those. No medals, no headlines, just understanding, and lives saved because of it. The Liechtenstein radar is long gone, its glass tubes dust on museum shelves, but Jackson's method endures. In every engineer who tests under real conditions, in every analyst who suspects that somewhere inside the machine a tiny resonance waits to be found. Test everything. Trust nothing unverified. Because sometimes the difference between life and death is measured not in miles or minutes, but in hertz.